When simulating a digital system, you can create in Verilog two types of delays. I'm not sure if they have any standard symbols. We can have a transport delay, which is an ordinary delay, and we can have an inertial delay, which swallows short pulses. Let's assume that both my delays are 2 nanoseconds in duration. We are going to put this signal in to both our delays and see what comes out. So we start at time 0, 3 nanoseconds later, we move to 1, 3 nanoseconds later, back to 0, 1 nanosecond later to 1, 1.5 nanoseconds later, back to 0, and then it remains 0. If we are not told anything, then when we first start off, we don't know what the output of the delay is going to be, because it depends on the past, and we're not told the past. So up until time 2 nanoseconds, because it's a 2 nanosecond transport delay, I don't know what the output's going to be. And then a transport delay, I simply shift everything by 2 nanoseconds. So this point gets shifted by 2 nanoseconds, this point gets shifted by 2 nanoseconds, and so forth. So notwithstanding my drawing abilities, we're going to have something that goes up here, across here for 3, down for 1, up for 1.5, and then down again. So it's simply a shifted version of what we see in red. There are two ways of determining the output of an inertial delay. The fast way is to simply copy what you get for the transport delay, except we're going to leave out any short pulses. Pulses strictly less than 2 nanoseconds will be omitted. If something's exactly 2 nanoseconds, we include it. Anything less than 2 nanoseconds gets omitted. We've got a pulse here of 3 nanoseconds, one here of 3 nanoseconds. This 1 second pulse is less than 2 nanoseconds, so this is going to be omitted. This 1.51, well, yes, it's smaller than 2 nanoseconds, so it's omitted, but since we're going to be at the value of 1 here, then the output is still going to be a 1 over here, as we'll see presently. Okay, so we simply copy the transport, we copy this one, we copy this one, we ignore this one, which means we stay what we're equal to. This is what I was trying to explain before. In some ways we ignore this one because it's 1.5, but then we're already at 1, so we're not going to move, so we keep it up here. So whether you think we ignore it or we don't, it doesn't really matter. We get the same answer here. And then since this one here goes for longer than 2 nanoseconds, we include it down here. Doing it this way, for example, trying to explain what happens here is a little bit clumsy, so therefore there's another way which is a little bit slower, but it's very clear what goes on. The way we do it is we have some yellow post-it notes, our to-do notes if you like, or a little table here with time and value to make the output. And we're going to write down things to do in the future. Inertial delay, start off same as before, 2 nanosecond delay. We don't know anything about the past, so unknown here for 2 nanoseconds. Okay, the input A at time 0 is 0. So we write a to-do note to ourselves. At time 2 nanoseconds, we are going to make the output 0. And then we run forwards in time. So we go forwards, we go forwards, we go forwards. We get to 2 nanoseconds. And the input hasn't changed. And our to-do list tells us at time t equals to 2 nanoseconds to make the output 0. So we dutifully make the output 0 at 2 nanoseconds. And we keep going forwards. We get to 3 nanoseconds. And we've done this, so we can cross this off. We get to 3 nanoseconds. the input changes, so we make another to-do note. Since the input changed at 3 nanoseconds, then we want at 5 nanoseconds to change the output to A1. So at time 5, change the output to A1. We don't do anything yet. This is a to-do note to our future selves to do something later. And we keep moving forwards in time. So as we move forwards, we just keep outputting the same value as before unless we're told otherwise. We keep going, we keep going, we keep going. We get to this point here, which is at 5 nanoseconds. The input hasn't changed. Our output's going to be constant all the way up to here. We have our to-do note. It says, make the output A1. Okay, fair enough. Let's make the output A1 here. Now we keep running forwards. The input changes at time 6 nanoseconds. We've done this at time 6 plus 2 nanoseconds, 8. We should change the output to be a 0. Run forward some more. Keep the output constant. We get to this point here, which is at time 7 nanoseconds. Because the input changes, we need to make another to-do note. The basic rule though is we only have one to-do note. Because I'm about to create a to-do note, I delete the old one, and that's where the inertial delay comes in, and create a new note at time 7 plus 2 at 9 nanoseconds. I make the output A1. Now I run through this. I get to time 8.5. I haven't got any to-do notes that have expired, so the output stays constant all the way up to time 8.5. My input changes again, so I create another to-do note, and my rule is any existing to-do notes get eaten up, so that disappears at time 8.5 plus 2 nanoseconds, so at time 10.5 I make the output A0. And that brings me, and then I run forwards again until I get to time 10.5. Then my to-do list tells me to make the output 0, and I get this. So the first way is faster, and once you know what you're doing, you just first do the transport delay, then get rid of any short pulses. But it's a little bit tricky to explain, so this to-do note is a very systematic way. This is how a computer would do it if you had to program it into the computer. How might I use these delays in a simulation? So these are just for simulation, and they're not modelling very accurately what happens in an FPGA, but they're crude approximations that have the benefit of being able to be simulated quickly. And we have a hierarchical range of tests when we're developing digital systems. We want silly errors to be caught very quickly. The comprehensive tests might take hours or days to perform. We want to be able to perform fast simulations beforehand just to make sure we haven't made a silly mistake. So for such fast simulations, we can use a transport delay to model, for example, the output of one lookup table going to the input of another lookup table on the FPGA. In other words, the wire delay. So we haven't looked at why wires introduce delays yet or by how much, but they are significant, and we can use a transport delay to model the time it takes a signal to propagate down a piece of wire inside the FPGA. For an inertial delay, they are commonly used to model a logic gate. So if I have an AND gate here, the output is not going to change immediately in the real world. I could use a transport delay, but another phenomena occurs. We'll learn later in the course why this is true, but if you really want to know beforehand, then you can think about, in order for this logic gate to work, I need to be able to change the internal voltages inside this. If I apply a very brief pulse, then there's not enough energy here to charge up or discharge the internal capacitance of this logic gate, and hence it's not going to know that the input's changed. if the input is a sufficiently small pulse. So that means that people normally model a logic gate in a crude way by using an inertial delay at its output. The effect of this is that if the input to our logic gate is a very brief pulse, then we're not going to notice any change to the output. Only inputs whose duration is greater than or equal to the inertial delay are going to have an effect on the output here. If you're asked to draw a timing diagram of this, then you just do it in 2 steps. First, you work out the waveform here using a timing diagram for an ideal logic gate, and then you simply take the waveform here and put it through the inertial delay like we looked at just before. This is not a realistic model, but it is sufficiently useful that we can get fast simulations that serve as a first check whether our digital system might work or not. It's natural to ask how this relates to contamination delay and propagation delay. The first thing is that propagation and contamination delay are not true delays. They're just timing abstractions. So they're different things entirely. Transport delay and inertial delay are actual idealized elements we can insert into our simulations. We can't synthesize them. You can't build this into FPGAs, but we can simulate them as idealized representations of what's going on. The contamination delay, propagation delay, timing abstractions of a real-world logic gate are a more refined description of how logic gates actually work. We can go the other way and ask, if we were to build this hypothetical logic gate, what would its contamination and propagation delay be? And it's quite easy to give an answer to this. If you look at the timing diagrams, then you'll find that both the contamination delay and propagation delay will be equal, and they will both equal the inertial delay that we use here. Lastly, we can look quickly at how to implement this in Verilog. And I emphasize these delays are just for simulation, not for synthesis. For an inertial delay, we use an assign statement and we put the delay at the start, and then we can do y equals x. If we want to have an ideal logic gate followed by an inertial delay, that would be following the same pattern, y equals x or z, for example. So that's for an inertial delay. For a transport delay, we would use an always statement, and we would have y, and it's crucial we use a non-blocking assignment rather than just an equal sign here, and put the delay in here. Now, there are many ways of writing statements with delays. You'll find that you can put this #2 out the front, you could make this an equals, you could probably put this #2 in here and so forth. Any of these other combinations are going to give you something that's wrong. It compiles, it does something, but it does not do what you expect. So this is probably the one case when I recommend you just memorize how to do this in Verilog.